Okay, thank you. I'm an undergraduate student at the University of Victoria in Canada, and I've been working on this project with Dr. Colin Goldblatt and Dr. Kelly McCusker over the past year, and I'm really excited to be here today and be able to share what we found with you. So as a bit of background, the faint young sun paradox refers to a long-standing question in paleoclimate about what kept the Earth warm early in its lifetime when the sun was dimmer than it is today. So here we can see a chart showing the age of the sun in billions of years along the x-axis. And during the Archean, the sun was about 20% dimmer than it is today, and so there was less radiation reaching the Earth. Radiative forcing is one way to measure the amount of energy in the Earth's system. And it is commonly used in studies of anthropogenic climate change. And it refers to the difference at the tropopause between the sunlight absorbed by the Earth and the amount of energy radiated back to space. So with 20% less sunlight, there should be about 50 watts per square meter of less radiative forcing than we experience today. And because surface temperature is proportional to radiative forcing, that means that we expect that the Earth would have been much colder. However, geologic evidence suggests that that wasn't the case, and there wasn't widespread glaciation, and so the Earth must have been roughly similar in temperature to how it is today. And so then the question remains, what made up that 50 watts per square meter of radiative forcing that's missing from the energy budget? A lot of previous studies have focused just on greenhouse gas amount in the atmosphere or on biogeochemical feedbacks, but here we're looking at physical processes that are acting on the climate system itself to resolve it. So our hypothesis is that during the Archean, there were less stratus clouds, and that allowed more sunlight to reach the surface of the Earth and be absorbed, and therefore we'll need less carbon dioxide in the atmosphere to keep it warm. Stratus clouds typically form under an inversion, where shallow convection lifts moisture into the atmosphere. And with a stronger inversion, the troposphere is more stable, and a rising air parcel is colder than the air above the inversion. And so when clouds form, they stay trapped at the boundary layer. This photo was taken in Marin County in California, and it's looking down over the top of stratus clouds that have been trapped under an inversion like that. The strength of the inversion can be measured by a metric called lower tropospheric stability, or LTS, and that's the potential temperature difference between the surface and 700 hectopascals. It's shown here at the top of this diagram of the structure of the atmosphere. So in the Archean, we expect that a weaker inversion would result in less clouds, therefore allowing more sunlight to be absorbed by the planet. And we think that that might contribute enough additional heating to prevent glaciation. So to test this, we used NCAR's Community Earth System model with CAM4 and a slab ocean using a 1.9 by 2.5 degree grid. And the model was run for 40 years total. Equilibrium was reached after 20 years. And so all of the following figures show model output averaged over the final 20 years of the run. Everything was configured with modern day values, except that we lowered the solar constant and increased the CO2 such that the surface temperature stayed within 0.5 Kelvin of the present day control run. And so by setting the experiment up like this, we're not actually trying to simulate conditions in the Archean, but we are doing a controlled experiment to try to determine how clouds change when we're systematically changing the way that the atmosphere is heated. All right, so we've got a few slides that are laid out like this, where we've got present day on the top left, with this one's cloud fraction, and so more clouds are in white and absence of cloud is in black. And then we have the Archean with 80% of the present day solar constant on the right. And you can see that in the present day, then the areas where we see the most stratus clouds is off the coast of the continents and the downwelling limbs of the Hadley circulation. and that is where the biggest changes in the Archean. At the bottom here, we see the difference between the two time periods, where purple indicates a reduction in low cloud amount and green indicates increase. And so again, we see that globally there's a reduction, but again with the strongest difference in the areas that we see the most clouds in the present day. Here we have planetary albedo, again with present day on the top left and the Archean on the right. And again, difference between them on the bottom here, where again, purple indicates a reduction in the global albedo and orange indicates an increase. And again, we see a fairly consistent reduction in the albedo of the planet worldwide. This one is shortwave cloud forcing, and here we see the biggest difference between the present day and the Archean. And in the difference field on this one, the orange indicates that there is 20 watts per square meter of additional forcing worldwide that is able to be absorbed by the planet with this reduction in clouds. So in these figures, on the left we've got cloud fraction plotted against solar constant, and on the right we've got cloud forcing plotted against solar constant. And each individual point that you see corresponds to an individual model run where the solar constant was a percentage of present day, and the carbon dioxide was adjusted so that it gives the same average global surface temperature. So if we look at the red circles, that is low cloud amount, and we see a very consistent, steady reduction in cloud fraction as we turn down the solar constant and go back in time. And the shortwave cloud forcing is associated with low cloud amount, and we see an increase in the amount of forcing that's absorbed by the planet as we go back in time. You can see that there is a increase in the amount of high cloud as we go back towards the Archean, but the associated long wave cloud forcing, there's not nearly as significant a change there, so that doesn't contribute as much to the energy budget as the shortwave cloud forcing, which is what we're interested in. All right, so to talk a little bit more about the mechanism for the results that we're seeing, we're making two changes to the model. We're decreasing the solar constant, which means that we're heating the surface less. Less surface heating means less evaporation or latent heat flux, and this is going to result in less moisture in the atmosphere. So just with that change alone, there's going to be fewer clouds. But we're also adding more carbon dioxide to the atmosphere, and an atmosphere that contains more greenhouse gases is going to emit more radiation, so it's going to cool, and that's going to weaken the inversion. I mentioned that the strength of the inversion can be measured by lower tropospheric stability, which again is the potential temperature difference between the surface and 700 hectopascals. And a similar metric was introduced by Wood and Brotherton in 2006, and that's the estimated inversion strength. And both the lower tropospheric stability and estimated inversion strength are correlated with stratus cloud fraction. Here we can see that there's a fairly linear relationship between lower tropospheric stability and cloud fraction, and estimated inversion strength, there's even stronger correlation with cloud fraction. So in our experiment, here we have lower tropospheric stability plotted in black and estimated inversion strength in blue, and both of them decrease steadily as we go back in time towards the Archean. And so this is what is resulting in the lack of clouds. In this plot, we can see that we also have a few results plotted from CAM5, which is the newer version of the atmospheric model, and it uses a different parameterization of stratocumulus fraction than CAM4 does. And so that was encouraging to see a similar trend in our preliminary results there, which tells us that what we're finding isn't just an artifact of the way that the clouds are parameterized in CAM4. Okay, so because of this additional stabilizing feedback that we found, we ended up needing much less carbon dioxide than we expected. Our initial calculations were expecting us to need about 80,000 parts per million of carbon dioxide in the atmosphere to keep the surface temperature the same, but we ended up only actually needing 30,000 parts per million, which is a very significant decrease. And although we kept the global average surface temperature the same as present day, the spatial distribution of heat was quite different. Here we have the Archean, and the poles were about 8 Kelvin warmer than present day, and the tropics were about 2 to 3 Kelvin cooler. And again, in the Archean, what we're interested in is preventing glaciation, so warmer poles and cooler tropics helps with that as well. All right, so here we found that there is a physically motivated stabilizing feedback that comes into play when clouds cloud are reduced, cloud albedo is reduced, and this provides 20 out of the 50 watts per square meters of radiative forcing that was missing from the energy budget. And so in addition to that, the temperature gradient weakens, which further prevents glaciation. So without even needing to take biogeochemical feedbacks or other processes into account, we've already provided 40% of the forcing required to solve the faint-young sun paradox. Thank you.
Thanks, Victoria. So we have a few minutes for questions.
Yeah, it's a very interesting talk, but I'm sorry, I think your experiment is flawed because you try to simulate the Earth's atmosphere, what happened 2.5 billion years ago, but you use NCAR-CAN model, and you only change its solar constant. But how about like surface vegetation and water vapor amount? You didn't change.
No, we didn't change any of that. So
that's right. So that's flawed because that's
yes.
not Earth's atmosphere 2.5 billion years ago.
Yes, exactly. And so again, we're talking about the Archean because we know that that's a different time period that had less sunlight. And here we were trying more to do a controlled experiment to see what the effect of changing the way that atmosphere was heated had on the clouds, and so that feedback is an additional contribution that could be used in further studies that better simulate the Archean, and then take that into account. But here we weren't actually trying to simulate that particular time period. Yes. Yeah, and so again, the spatial distribution that we saw might be different, but we would still expect that in regions where stratocumulus fraction is decreased, we would see the same changes that we saw here.
Oh, thanks. Yeah, I really like the talk, and I think it's great research. First question was, when you went to the Archean, did you change anything about the cloud condensation nuclei or anything else, or is it all just the same? Okay, interesting. So you really isolated the solar constant feedback. And second thing, do you happen to remember what the change in the global mean planetary albedo was when you went from current solar constant to 70% solar constant?
Yeah, the global mean, it was about 3.7%.
Okay, thank you.
Yeah.
Question. Just, I know you didn't do it here, but do you have any inkling on the effects of the continental configuration if you change it to, whatever paleo reconstruction of that back in the 2.9 giga years? How would that change your results? Do you have any clue on that? I'm
not sure how it would change the overall trend in terms of that. Obviously, the cloud distribution would be different. The ocean, again, we were only using a slab ocean model here too, so the whole ocean circulation would be different as well. But again, we would expect that if there was still enough atmospheric circulation to have inversions, that those would probably weaken because of this trend that we saw with the lower tropospheric stability. And so weakening inversions is going to result in less stratus clouds, wherever spatially that might be.
Hi. Great job. I think it was the correct experiment to do for what you're doing. The shortwave cloud radiative forcing, I just had a kind of a question about that, or more of a comment. But it's a dicey concept because you can change cloud radiative forcing without changing clouds. When you change the insolation, when you change surface albedo based on the way it's defined. So it might not be the best metric for evaluating or isolating the influence of clouds. It's useful, but there are better ways in the literature of quantifying the role that clouds affect the difference between clear and cloudy sky radiative fluxes.
Okay.
Right. I think in the interest of time, we should probably move on to the next speaker. Thanks very much, Victoria.
Thank you.